And now I will introduce our next speaker, Dr. Alejandro, who would be discussing irrigation management of the grain and sorghum under full and deficit irrigation. So let me tell briefly about Dr. Alejandro. So Dr. Manuel Alejandro is an assistant professor in water and irrigation management at the Department of Agriculture, Veterinary, and Rangeland Sciences at the UNR. He received his doctoral and master's degree in agriculture and biosystems engineering from the University of Arizona and BS in irrigation and engineering from Mexico, his country of origin. Before joining UNR, Alejandro worked as a research engineer with Texas A&M in Amarillo, as a postdoc fellow with the USDA ARS in Bushland, as a graduate research assistant at the University of Arizona, as an irrigation engineer with the Mexican National Institute of Water Technology in Mexico. So a lot of experience on irrigation. Alejandro Research Program at UNR has the overarching goal of developing knowledge that will improve the management of irrigation water resources used in arid and semi-arid areas. Among his current research interests are precision ag, deficit irrigation, irrigation scheduling methods, plant and soil water sensing systems, crop modeling, decision support systems, and the application of artificial intelligence to irrigation water management. So again, thank you for joining us this morning. So I would pass to Dr. Alejandro to take over.
Thank you, Maninder. Thank you very much for the introduction, and thank you for inviting me. So this presentation, it's about irrigation management of grain sorghum under full and deficit irrigation. And I want to start this presentation with this quote that states that without appropriate management, irrigated agriculture can be detrimental to the environment, and even it can endanger sustainability. My interpretation of this quote is that in order to take full advantage of the benefits of irrigation without causing any damage to the environment, we need to make sure that we follow appropriate irrigation management practices. And the main topic that I want to talk to you about is how we follow good irrigation management practices in order to achieve precise levels of irrigation that were required by an experiment that was conducted at the Valley Road Experiment Station lab here close to our main campus at UNR. So when we need to irrigate, we need to irrigate when the precipitation is not enough to satisfy the water needs of a crop. And this happens to be the case in the entire state of Nevada. And also most of the Western United States. Pretty much the rainfall that it's received during the growing season in this area is just not enough to support any type of significant yield. So that's why we rely on irrigation, and that's why we need to be very careful in terms of conserving the water that we use for irrigation. Now, when we start to irrigate, um, water starts entering into the soil and starts filling the empty pore spaces in the soil. So we can think of the soil as a sort of water reservoir. And there are three levels that we need to be aware of and understand in order to make good irrigation management. The first of those levels is what it's called the saturation point. This is the point that is reached when we start to irrigate to the point where all the pore spaces are filled with water. So when that happens and we continue irrigating, then because the soil cannot take any more water, then we're going to start to see some ponding on the surface of the soil. When we irrigate above the point of saturation and we have those ponds, eventually we may see runoff. And when we see that runoff, that's an indication that we are over irrigating and we are not making a good use of that water. And that runoff can be also mixed with agrochemicals. And then it may, as it follows downstream, it may contaminate downstream water resources. So this is part of what it's meant by saying that irrigation can be detrimental to the environment if we are not careful with the way that we irrigate. So that's the first point, the saturation point. The second level, it's what it's called field capacity. So when we irrigate to the point of saturation and we stop irrigating, then the water will start to be drained by the force of gravity. And after approximately 8 hour, I'm sorry, at approximately 48 hours after we reach that saturation point, the water level in the soil will reach the field capacity. So the field capacity is the volume of water that remains 48 hours after irrigating to the point of saturation. So that field capacity represents the amount of water that can be stored by the soil against the force of gravity. Now, how this happens, or the reason why this happens, or why the water remains attached to the soil, opposed to the force of gravity, it happens because water likes to stick to soils, to soils and to any solids. So in the same way that when you wash your hands, and even after you wash your hands and you shake that water, you have after that you still have some water drops, in your hand. So the same happens in the soil. That soil, the force of adhesion of the soil allows the water to remain stick to the soil. So if we were to stop irrigating once we are at field capacity, what is going to happen is that the crop roots are going to start suctioning the water from the soil, and there is also going to be evaporation at the top of the soil, and that combined effect is what we call evapotranspiration. That evapotranspiration is going to start consuming the water in the soil, and if we were to completely stop irrigating, then the soil will eventually reach what is called the permanent wilting point. This is a point at which the plant can no longer, does not have enough force, the roots does not have enough force to get the water from the soil. So the what we call the available water capacity, or the water in the soil that it's readily available to the soil, is the difference between the field capacity and the permanent wilting point. So what I want to point out from this slide, and kind of like the take-home message that I want you to get, is that when we irrigate above the field capacity, we are making a poor use of the water, because that water will be either lost by runoff, or it will be lost by drainage. So every time that we irrigate, if we want to do good management, we have to make sure that we only irrigate to the point of field capacity. Now, so this presentation, it's about full irrigation and deficit irrigation, but what I mean by that? By full irrigation, I mean to irrigate the amount that it's required by the crop to avoid any water stress. And as I will show, that water stress will cause a reduction in yield. How we can implement that full irrigation? Well, we can do that with two steps. The first one is to make sure that every time that we irrigate, we replenish the soil water content in that water reservoir to field capacity. So that's one step. The second step is that we need to make sure that we irrigate before we reach a maximum threshold of depletion of that available water capacity. So full irrigation does not mean that the soil always have to be at field capacity. So there is still some water, so some volume of water that can be depleted by the crop. But what we need to make sure is that we are not depleting all that available water capacity content beyond a maximum threshold. Now that threshold is different for different crops. That changes depending on the crop. But in the case of grain sorghum, as we can see from this table taken from the FAO irrigation and drainage paper number 56, which is a very good reference for anyone interested in doing good, following good irrigation management practices. So that report tells us that we can allow the available water capacity to be consumed at about 55% without experiencing any water stress. So again, we can let the soil water between the field capacity and the permanent wilting point to be consumed up to 55%. And if we allow that, still the crop will be experiencing no stress whatsoever. But if we allow the available water capacity to be depleted beyond that 55%, then that's when we are going to experience that water stress. Now, what I mean by deficit irrigation, it's basically to irrigate less than the amounts that are required for full irrigation. And the way in which we can implement deficit irrigation is by irrigating a percentage of the amount that will be required to replenish the soil water content in the root zone to fill capacity during each irrigation. And the percentage of deficit irrigation that we use is going to determine the severity of the water stress, and it's also going to determine the impact that we are going to have on the yield. These are some yield results obtained from an experiment conducted in the Texas High Plains during 2 years, 2012 and 2018. So grain sorghum was subjected to three different deficit irrigation treatments, 80, 50, and 30%. And as you can see, in both years, we had a reduction in the yield that follow a linear trend as we reduce the deficit irrigation levels. So then the question is why, if we are going to experience yield losses when we apply deficit irrigation, why we want to even consider this possibility? Well, the reason is not that we want to, uh, to practice deficit irrigation. The reason is that many producers are currently being forced to practice deficit irrigation. And it's likely that, so we are in the most arid state in the country. And Nevada is also one of the states that is experiencing the highest population growth. So water is going to become more and more valuable. And then more farmers and more producers are going to be required to practice deficit irrigation, whether we like that or not. So we want to be prepared for that scenario. And, um, and then since as the water becomes more valuable, we have to change the paradigm of irrigated agriculture. Instead of focusing on maximizing the crop yield, we need to think on ways of maximizing what is called the water use efficiency. And this is the amount of yield that is obtained per unit of water applied to a crop. And as we can see, the formula to obtain water use efficiency, it's very simple. But from this formula, we can realize that we can improve the water use efficiency only through two ways. The first way is to increase the yield, or the second one is to use less water to produce the yield. But as I just showed, these are mutually exclusive options, because when we use less water, we are also decreasing the yield. But still, this does not prevent us from trying to find alternative crops like sorghum, that, as Dr. Walia described very well, it's a naturally drought tolerant crop. So we can try to find crops that allow us to produce, even maintain the yield, or that can ameliorate the reduction in the yield that we're going to have by being forced to use less water to irrigate. So with these ideas in mind, we conducted an experiment where we subjected grain sorghum to three irrigation deficits, three irrigation treatment levels. The main objective of this experiment was to evaluate the response of two grain sorghum cultivars to the following treatments. The first one was full irrigation. That means to replenish 100% of the soil water depletion to field capacity. The second one was a moderate deficit irrigation, and that was achieved by replenishing 60% of the soil water depletion to field capacity. The third one was severe deficit irrigation treatment, and that was achieved by replenishing 30% of soil water depletion to field capacity. The way in which the response of the two grain sorghum cultivars to these irrigation treatments was evaluated was by evaluating the response to water stress based on phenotypic drought-resistant traits, and this was the focus of Dr. Yerka's research group, and then also to evaluate the response to water stress using remote and proximal sensing systems, and this was the focus of Dr. Washington Allen's research group, and he's going to show some results in that regards later. But so my contribution to this project was to make sure that these three different irrigation treatments were achieved. So here's a layout of the experimental setup for this experiment. So there were 9 blocks resulting from 3 irrigation treatments and 3 replications. So these blocks were randomized, and inside of each block, there were 2 plots, one with a white sorghum plot, and a red sorghum plot. And there was also an alley in between them. All the blocks had an independent irrigation, and they were irrigated with a drip irrigation system. So we were able to control the irrigation individually of each of these plots with some valves, and I will show how we did that. Um, and we also installed 3 soil water sensing stations, and these are represented by the blue circles. And the data that was collected every hour from these soil water sensing stations allow us to know how much water we needed to apply to each block in order to satisfy the irrigation treatments that were assigned to each plot. Now, in order to be able to achieve those 3 irrigation treatments, we had to apply what I called the 7 minimum requirements for a good irrigation management, or more precisely for the 7 minimum requirements for a very precise irrigation management. The first of these requirements is to have a well-designed irrigation system. The second one is to have a well-managed irrigation system. The third one is to have availability of weather data, more precisely of the weather variables that affect evapotranspiration. The fourth requirement is to have a way to quantify how much water we have in the soil. And we do this by installing at least 1 soil water sensing station, preferably in a location that is representative of the predominant conditions that we have in the field. The fifth requirement is to have soil information. The sixth one to have information about the crop. And the seventh is to have an irrigation scheduling method that integrates all of this information and then uses that information in order to determine when we need to irrigate and how much we need to irrigate. So regarding the first requirement, having a well-designed irrigation system, well, one way to know if an irrigation system has been designed properly is to assess its uniformity. Uniformity means that in the case of a drip irrigation, any 2 emitters in a block should be applying about the same amount of water. There can be only about 10% difference in the flow that is delivered by any 2 emitters in a block in order to make sure that we have satisfactory uniformity. So in order to make sure that we had a drip irrigation system with a good uniformity, we perform what is called a catch-can test. This consists on using placing some containers below emitters inside a block, and then leave these containers for a given period of time, and then measuring how much water was delivered by each emitter. So by doing this in the very first, one of the very first emitters inside of a block, and then putting a container in one of the last emitters in a block, we were able to determine whether there was a good uniformity. And it turns out that the flow that was delivered by any two emitters in a block were within a 10% difference. So that led us to conclude that the irrigation system was well designed. And I must point out that this was not the merit of having a well-designed irrigation system goes to our technician, Scott Hoover. He's the one that designed the irrigation system and installed the irrigation system. I provide some advice, but the merit goes to him. Now, regarding the second requirement, having a well-managed irrigation system, in order to know whether we are managing properly an irrigation system, we need to have a water measuring device or a system in place that allows us to quantify how much water we are applying to a field. In this case, we put a pressure regulating valve at the beginning of each of the 9 blocks that we had. The reason why we put this pressure regulating valve is that allow us to have an almost uniform pressure of 10 psi for all the emitters within a block. For drip irrigation system, the emitter that is delivered by a drip emitter, it's proportional to the pressure that it's received by the emitter. So by having those pressure regulating valves, we were making sure that each emitter was applying approximately 0.17 gallons per hour. So that's what, with those pressure regulating valves, we were able to control how much water was being delivered by each emitter. But the other component in our that we needed in order to make sure that we were irrigating the volume that we needed for each block, in order to do that, we installed these battery operated timers. These timers allow us to enter a certain time, and then the valve will be open for the given amount of time that we indicated in the timer. So that allowed the drip irrigation system to be irrigating only during the amount of time that we needed in order to achieve the irrigation amount that we wanted to apply to each block during each irrigation. Now, regarding having the data, weather data available, right next to the experimental plot, there is a weather station. And this weather station collects air temperature, solar irradiance, wind speed, and relative humidity, which are the variables that we need in order to estimate the reference evapotranspiration. And this information, it's available through a website. The weather station is maintained by the Desert Research Institute, and it's hourly data collected by that weather station it's available to the public through a website. So we were downloading periodically during the growing season these sets of weather data collected every hour by this weather station. So regarding the fourth requirement, having a way to quantify how much water we have in the soil at any given time. In order to do that, we installed 3 saltwater sensing stations. We installed 1 sensing station for each irrigation treatment. This sensing station consisted of 3 time domain reflectometer soil moisture sensors that look like this one. And these were installed at three depths, 15 centimeters, 30 centimeters, and 60 centimeters. So at about 2 feet, and the deepest one was at about, sorry, the deepest one was at about 2 feet, and the middle one was at about 1 foot. So the way in which these soil water sensors work is that an electric impulse is sent by a data logger through a cable, and then it's sent through a rods, and these soil water sensors are buried in the soil, and I will show how we did that. But when the electric impulse travels through these rods, it goes back and forth, and the time that it takes that electric impulse to travel allow us to know how much water is in the soil, because in wet soils, the electric impulse will travel faster than in a dry soil, because the water, it's a better conductor than air. So that's the way in which these TDR, or time domain reflectometer soil water sensors work. Now, when we installed the soil water sensor, we were very careful on making the smallest possible hole in the ground, in order to try to disturb the soil as minimum as possible. And as you can see, this is an image showing the probe inserted at 30 centimeters. This is a probe inserted at 60 centimeters, and you can see the the rod, it's all the way inside of the soil. So we installed these three probes in each of these saltwater sensing stations. And these sensors were collecting data every hour. And that data was stored in a data logger. And that data logger sent that data to a gateway. And these are Internet of Things capable sensors, um, that that information that was collected every hour by the data loggers was then sent wirelessly via satellite to a web storage service, and then we were able to access that data remotely from a computer in the lab. So that way we didn't have to go to the field every day to collect the data. We can do that from our desk. Now, regarding the fifth requirement, having information about the soil, we were able to determine the field capacity of the soil by irrigating the first time beyond the point of saturation, and then leaving the soil drain. And then after approximately 48 hours, we look at the water content after those 48 hours, and we use that as a measurement of the field capacity that we had at the three different depths. So this is this graph shows how the volumetric water content was changing at the three different depths, where we put soil water sensors in the full irrigation in the saltwater sensing station that we put in a block where we practice full irrigation. So all these jumps that you see in the graph represent points during the growing season that when we applied irrigations. And you can see that at 15 centimeters and at 30 centimeters, because we are closer to the surface, then we have a higher variation, especially at the beginning of the growing season. But then the variation, especially at 60 centimeters, because it's deeper in the ground, that variation wasn't as significant as it was in the top layers of the soil. But this is how we got the field capacity. In addition to getting information about the field capacity at the different depths, we also access data from the NRCS Web Soil Survey. This is a website that allows anyone to go and look at the characteristics of a field. In this case, so this is the field where we conducted the experiment, and the dominant soil there, it's an ore sandy loam with 0 to 2% slopes, and it has a typical soil profile from 0 to 10 inches, it's a sandy loam. From 10 to 50 inches, it's a sandy clay loam. And from 50 to 62 inches, it's a gravely sandy loam. Um, the, from this database, we were also able to estimate the available water capacity that was about 0.145 inches. So that allows us to know how much, when we already knew where was our field capacity, but then based on this information, we were also able to determine where was our permanent wilting point. So the sixth requirement is to gather information about the crop. For irrigation purposes, the most important information is the root, how the root depth changes over time. Because when we irrigate, we want to be irrigating the entire root zone. And we are also interested about the crop, how the crop coefficient changes over time. This crop coefficient allows us to know or to estimate the evapotranspiration that we have in the crop by multiplying that crop coefficient by a reference evapotranspiration that we can calculate from the weather data that we obtain from a weather station. From that FAO 56 report, we were able to determine that the maximum root depth of the grain sorghum was from 1 to 2 meters, and the crop coefficients at the beginning of the growing season was 0.3. At the middle was between 1 to 1.1, and by the end of the growing season was about 0.55. So as we were collecting soil water sensing data, and we were measuring or estimating how much water was being consumed by the crop every day, we were also monitoring or estimating how much water was consumed by the soil by applying this formula um, to estimate the evapotranspiration. The seventh requirement is to have an irrigation scheduling method in place. And our irrigation scheduling method was a spreadsheet that where we will enter the soil water contents collected right before irrigating. And based on that, the spreadsheet calculated automatically the irrigation amounts that we needed to apply. So this table shows the irrigation amounts that were applied for the 9 blocks. And in the first irrigations, the first 3 irrigations, in order to promote a good germination, we apply the same amount to all the blocks. But after that, the irrigation started to be determined by the irrigation treatment and also by the measurements that we were obtaining from the soil water sensors. Now, how can we know whether we were successful in terms of avoiding water stress for the full irrigation? So this graph shows the volumetric water content, how that water stored in the soil change at the 3 depths where we put the soil probes. So at 15 centimeters, the volumetric water content is represented by the red line. 30 centimeters, the volumetric water content is represented by the blue line, and at 60 centimeters by the green line. So again, these jumps in these time series represent the times when we applied irrigations. But the yellow time series here represent the average soil water depletion that we had in the soil. And as I mentioned, in order to avoid water stress, we needed to make sure that that soil water depletion was below the maximum threshold of 0.55 in order to make sure that we were causing no water stress to the grain sorghum. And as you can see, for full irrigation, that soil water depletion time series was below 0.55 during the entire growing season. So this is how we know that we achieved that full irrigation, or in other words, we had no water stress in the 3 blocks where we applied the full irrigation. Now, regarding the moderate deficit irrigation or the 60% irrigation treatment, the average soil water depletion there, as you can see, for most of the irrigation, of most of the growing season, we have that soil water depletion below that 0.55 threshold that is represented by the dashed line. Um, but there were some periods during the growing season where the soil water depletion was above that threshold. So that means that the crop, this grain sorghum, subjected to this moderate deficit irrigation, was indeed experiencing water stress, but that water stress was moderate because it only happened during peak times during the growing season. And as you can see, that usually happened before days before applying irrigations. Regarding the severe deficit irrigation or the 30% irrigation treatment, as you can see, by mid-July, the soil water depletion was completely above or way above the 0.55 soil water depletion threshold. So that means that we were able to apply severe water stress in the crop based on these management practices that I just showed. Now, here are some images that show how the crop look. This is the 100% or full irrigation grain sorghum. This is the 60% or moderate or grain sorghum subjected to moderate irrigation deficit. And this is the 30%. And you can see the big difference in the grain between the 100 and the 30, or between the 60 and the 30. But the drought tolerance of the sorghum uh, makes harder to see that big difference between the 100 and the moderate irrigation deficit. In terms of the seasonal water use, for full irrigation, we use a total of 32 inches. For the moderate irrigation, we use a total of 22 inches. And for the severe, we use a total of 15 inches. And these pictures were taken on August the 8th, about 78 days after planting. So we are going, oh, one thing, some of you may be thinking, well, what are the yield results? And we don't have accurate yield results because there was a significant beard damage, and Dr. Walia just mentioned that that's a problem that you need to be careful with. But we are going to continue this experiment this year and then the next year. So we hope to have some more accurate yield results in the future. But in addition to continuing that experiment with drip irrigation, we're also going to conduct an analogous experiment this year and the following in Diamond Valley in Nevada. But we, instead of drip irrigation, we're going to be using a center pivot irrigation system. This center pivot, it's located in the new UNR Great Basin Research and Extension Center in Eureka. And in that center pivot that we are going to use, we installed what is called a variable rate irrigation package. What that package allows us to do is to control the irrigation that we can apply with four individual sprinklers. So four sprinklers apply the same amount, and the following four sprinklers can apply a different amount. And that allows us to apply variable amounts of water to the field which will allow us to have a very easy way to apply this irrigation management treatments. And to the best of my knowledge, this is the very first variable rate irrigation package that has been installed in Nevada. So we are very excited to pioneer the introduction of this technology and start testing it there. Here is an image of a variable rate irrigation system used in the Texas High Plains to irrigate sorghum. Different irrigation treatments were applied here. And as you can see, there is a significant difference in how the cotton is looking based on the irrigation treatments. So what we expect to see it's also in those differences in the grain sorghum by applying different irrigation treatments. But in that case, the plots will look more like what you can see here on the left, rather than the rectangular plots that I just showed you. So I would like to acknowledge Dr. Melinda Yerka and her lab, Dr. Robert Washington Allen and his lab, my PhD student, Uriel Cholula Rivera, who also collaborated in this experiment, Maninder Walia and Gary McQueen, that are affiliated to UNR Extension. So with that, I'm done with my presentation.
Thank you, Dr. Alejandro. I appreciate that you was willing to be a part and presented a great talk. I think participants learned a lot about the irrigation management, especially in sorghum.
Thanks.
So moving forward now, we will have a break of about 10 minutes. And following the break, we will have our two speakers, Dr. Yerka and Dr. Robert Washington. So we'll see you at, it's about 10:40, so we'll be back at 10:50. Thank you. Thank you, everyone.